could a single, purely theoretical math proof really let someone just steal $200 billion in Bitcoin? I know, it sounds exactly like the plot of some crazy sci-fi heist movie. But in the realm of theoretical computer science, yeah, it is a dead serious question. Welcome to this explainer. Today, we're diving into a mathematical concept so incredibly profound that cracking it wouldn't just, break global finance, it would literally redefine the limits of human knowledge.
The Clay Mathematics Institute actually designated this as one of their Millennium Prize problems. They're offering a cool $1 million to anyone who can solve it. But as theoretical computer scientist Scott Aronson pointed out, and I love this, if you actually manage to solve this, the absolute last thing you'd need is the $1 million prize. Now, you usually hear this problem explained using simple Sudoku analogies. But today, we're bypassing all that. We are getting into the hardcore, formal mechanics of literally the hardest problem in computer science.
All right, Section 1, the mechanics of P versus NP. To truly grasp why this remains unsolved, we really have to step away from the abstract math for a second and look directly at the actual machines executing these algorithms. Looking at the history here, it's wild how these theoretical blueprints completely dictate the absolute limits of human progress. Back in 1936, Alan Turing defined the formal model of computation itself. Fast forward a bit to 1955, and we see mathematician John Nash writing a letter to the National Security Agency. He predicted that cracking complex codes would require an amount of time that scales exponentially. Then, boom, by 1971, Stephen Cook and Leonid Levin formalized the exact boundaries of this massive computational wall.
To really get what Nash was warning the NSA about, you just have to contrast polynomial time with exponential time. Let's say you have an algorithm running in polynomial time, maybe n to the power of 3. If you process 100 elements, it might take your computer, about 3 hours. Not bad, right? But if that algorithm demands exponential time, 2 to the power of n, processing those exact same 100 elements, that would take 300 quintillion years. Seriously. That right there is the visceral, hard math difference between, yeah, this is feasible and this is strictly impossible.
So this whole mystery really rests on our formal models of computation. Let's start with the baseline of our entire digital world, the Deterministic Turing Machine, or DTM. A DTM operates strictly in a straight line. At any given state, reading any specific symbol on its tape, its programming dictates exactly one valid next step. It's totally predictable. This linear machine gives us what we call class P. That's the set of tractable problems you can solve in polynomial time. Think of stuff like sorting a bunch of data or just finding the shortest route on a map.
But what if the machine wasn't limited to just that single path? Enter the Nondeterministic Turing Machine, the NTM. Now, forget the idea of a physical gadget or some cute little robot here. An NTM is really a mathematical bounds test. It operates sort of like a theoretical multiverse. At any given state, instead of just taking one step forward, it branches out. It creates this massive computation tree to explore all possible paths simultaneously. It's basically guessing answers across this gigantic tree until, bam, it finds one that works.
And this right here is the core physical difference. On one side, you have a deterministic machine following a single, linear, predictable path, taking a polynomial number of steps. On the other side, a non-deterministic machine functioning as this exploding, branching computation tree making a bunch of simultaneous guesses. Which brings us directly to class NP. Now, quick side note, a really common misconception is that NP stands for non-polynomial. Actually, scratch that. It definitely doesn't. It stands for non-deterministic polynomial time. Class NP basically represents the set of all decision problems where, if you unleash that branching, multiverse-style, non-deterministic Turing machine, it can actually find an accepting path to the correct answer before polynomial time runs out.
See, this creates a formal, mechanical bridge between guessing an answer and actually verifying it. Think of it like a three-step process. Step 1, if an NTM branches out and magically guesses the correct path, well, step 2, that path gets recorded as a certificate or a witness. Then step 3, once you have that certificate, a standard linear deterministic Turing machine can take it and verify that the answer is right, all within polynomial time. The big takeaway here is that being solvable by an NTM is strictly equivalent to being verifiable by a DTM.
And man, that leads us right to the ultimate formal question. Does P equal NP? Seriously, can every single problem that's solvable by a branching, guessing machine in polynomial time also be solved by a linear deterministic machine in that same amount of time? Operationally speaking, does the ability to guess non-deterministically really give us any fundamental computational advantage over a linear approach? If P actually equals NP, it would mean non-determinism is just a shortcut we simply haven't figured out how to code yet. Moving right along to universal translators, NP completeness, and the Cook-Levin theorem. To try and answer this big question, we reach the narrative climax of our computational history. In the 1970s, Stephen Cook and Leonard Levin proved that certain problems within NP essentially act as universal translators. The Cook-Levin theorem mathematically established that the Boolean satisfiability problem, usually just called SAT, is NP complete. And guys, what this means is absolutely staggering. Not only is SAT in NP, but every single other problem in NP can be reduced to SAT in polynomial time. It's like SAT encodes the very underlying logic of a Turing machine's computation itself.
Because of this reducibility, all these seemingly unrelated, notoriously difficult problems, they're all mathematically tethered together. You've got SAT in logic, the traveling salesman in routing, the knapsack problem in optimization, and, yep, even Sudoku in puzzles. If you can write a fast, deterministic algorithm for literally any one of these, surprisingly charming but brutal NP-complete problems, you've essentially written a fast algorithm for all of them. You would literally prove P equals NP.
Next up, the meta-mystery. Is it formally independent? So, decades of brilliant minds have tried and failed to find that algorithm. And this massive failure has caused researchers like theoretical computer scientist Scott Aaronson to pivot to a really fascinating meta-mystery. Could the whole P versus NP problem be completely independent of standard mathematics? Could it just be that our current systems of logic simply lack the tools to prove it either way?
Well, for Leibniz's theorem and the concept of oracle machines, researchers actually proved that standard mathematical techniques, like diagonalization, treat Turing machines as opaque black boxes. So you can construct a theoretical oracle A, where P equals NP, and an oracle B, where P does not equal NP. But because our standard proof techniques can't peek inside that black box, they are fundamentally insufficient to solve the problem.
However, Aaronson makes a really crucial distinction here. P versus NP is classified as a pi-2 sentence. Now, unlike abstract mathematical infinities, like the continuum hypothesis, which might just sort of float in some realm way beyond human experience, a pi-2 sentence is about physical machines. It's about bits and logic dates. This means P versus NP has a definite, objective, true or false reality out there in the physical world, even if our current mathematical toolkit just isn't strong enough yet to prove which one it is.
So let's just visualize the physical reality if it actually turns out P does equal NP. The consequences would be absolute. Our entire digital economy totally relies on this asymmetry. The fact that multiplying large primes is easy, but factoring them is incredibly hard. If P equals NP, boom, all public key cryptography instantly breaks. Someone could steal all the Bitcoin. But on the flip side, disease-carrying protein folding gets solved, global logistics and scheduling become perfectly optimized. Heck, even the discovery of new mathematical proofs could be entirely automated by computers.
But let's be real. Domain experts overwhelmingly assume P does not equal NP. And because of that working assumption, our society operates in this hardcore reality. We rely on heuristics, approximations, bounded errors. We have to build these massive global systems that find good enough answers, purely because we mathematically assume that finding the absolute perfect answer demands exponential time that would literally outlast the lifespan of the universe. The sheer scale of the stakes really comes down to this. We operate our entire digital infrastructure in the shadow of an unproven inequality. Every single secure message, every bank transfer, every piece of encrypted data, it all completely relies on the mathematical difference between a single deterministic linear path and a non-deterministic branching tree.
I really want to leave you with this final, provocative thought. We just assume these computational problems are fundamentally hard. But what if they aren't? What if the perfect algorithm to solve our greatest logistical and scientific challenges is just hiding in a blind spot of mathematics? The answer is out there, waiting in the mechanics of computation. Thanks so much for joining me on this explainer. Keep questioning the boundaries of what's possible.